Hi viewers, welcome to my class on mechanics of materials. In today's class, I'll explain the derivation of Lame's equation for a thick cylinder. As I explained in the starting class, a thick cylinder is one which withstands a larger internal fluid pressure, and an approximate classification for a thick cylinder is if the thickness is greater than 1/10 of internal radius, you can call it as a thick cylinder. The higher thickness is required to withstand this larger internal fluid pressure. So when a cylinder is subjected to larger internal fluid pressure, automatically the thickness of the walls should be designed to withstand this pressure, and thickness will be more. So classification generally is used based on the thickness of the cylinder. So if the thickness is more than 1/10 of the internal radius, we can call it as a thick cylinder. And for a thick cylinder, we need to use a different analysis. Okay, in thin cylinder, we assumed hoop stress is same on the inner walls and outer walls. Generally for a thick cylinder, the hoop stress or circumferential stress will vary from inside surface to the outside surface of the cylinder wall. And also we cannot neglect the radial pressure transmitted. So let us consider a thick cylinder with internal radius Ri and external radius R0, and the length of the cylinder is L, which is perpendicular to the screen. Now on this thick cylinder, we can consider a thin cylindrical shell at a radius R with a thickness dr. So I am taking a thin cylindrical shell. Okay, this colored annular ring is a cross section of the thin cylindrical shell which I have taken from this thick cylinder. So which is at a radius R with thickness dr. So the cylinder is subjected to internal fluid pressure Pi and external pressure P0. Due to this internal fluid pressure Pi and external pressure P0, there will be a pressure transmitted through the walls. So it is compressing. This pressure is compressing the cylinder walls, and this pressure will be transmitted, and during the transmission the pressure varies, and let us say that pressure transmitted to this inner ring is PR from inside, and there is a small variation for external pressure PR plus dpr. So the variation will be very small. dpr is the differential change in pressure. So PR is the pressure transmitted to this ring, and it is also subjected to external pressure PR plus dpr. So the difference will be very small because it's a differential thickness of the cylinder wall considered. Now we'll separately analyze this thin cylindrical shell. So this thin cylindrical shell which you have considered on a thick cylinder, and that thin cylindrical shell I have shown separately. So the transmitted pressure is PR from inside and PR plus dpr from outside. So let us take a horizontal section plane and consider the lower half of the cylinder, and due to this internal pressure there will be a vertically downward force. Okay, and due to this external pressure there will be a vertically upward force. So this force on a curved surface you can find out as pressure into projected area. So which direction you want to find out the force? We want to find out in the vertical direction, that is vertically downward direction. So perpendicular to that direction you project this curved surface, this inner curved surface, you project it, that will give a rectangle. So that is, I am taking the lower half and projecting that inner curved surface on a horizontal plane. So that will give 2r into 2r is the diameter, inside diameter, into length is L. So the projected area is colored hatched surface. So that is the projected area of the inner curved surface. So on the lower half, the pressure force from inside is pressure PR into 2RL. Now outside also pressure is acting, so that is PR plus dPr, that will give an vertically upward force, and that pressure into projected area. Projected area is this area. This area is 2R plus 2dr into L. 2R is inside diameter plus dr plus dr, that is 2dr. So 2R plus 2dr into L will give the projected area of the external curved surface. So upward force from outside is PR plus dPr into this projected area, that is 2R plus 2dr into L. So you can find out the net force, vertically downward force and vertically upward force. The difference will give the net bursting force. Okay. So if you take the upper half, the similar forces will be acting, one due to inside fluid pressure, one upward force due to external pressure, downward force. The difference in force will be same as this. So the cylinder will be subjected to forces like this. Usually inside force will be higher. Okay, so there will be a net force downward here due to the difference in forces. There will be a downward force, and on the upper half, due to the difference in pressure forces, there will be an upward force. So the cylinder will be trying to burst as a result of these forces, and the cylinder walls has to resist that force. So the cylinder wall here, okay, so the thickness of the wall is dr. Cylinder wall area which resists this force is dr into L this side and dr into L other side. Okay. Now let us calculate this bursting force first. Now the force due to these pressures, you can write force from inside PR into 2RL. So PR into the projected area of the inner curved surface is 2RL, and force from outside is PR plus dPr into the external curved surface projected area is 2R plus 2dr into L. So the net bursting force is the difference of these two. So PR into 2RL minus this. So PR into 2RL minus PR plus dPr into 2R plus 2drl. So PR 2RL. So if you expand this, PR 2RL, okay, first term, then PR 2drl, then dPr 2RL minus, okay, and so minus dPr 2drl, dPr 2drl. So I expanded this. Now PR 2RL minus PR 2RL, that cancels. You have minus PR 2drl minus dPr 2RL, and this term, since it's a product of two differential quantities, dPr and dr. Okay, dPr is the differential change in pressure, and dr is the differential thickness of the this thin cylindrical wall. Since the product of differential quantities are involved, this term is negligibly small. So we have neglected this term and we have written this minus PR 2drl minus dPr 2RL. Now this is the bursting force acting on this thin cylindrical shell. Now this bursting force is resisted by the cylinder wall, and this cylinder wall is resisting this bursting force. So that cylinder wall area is resisting areas dr into L one side and again dr into L on other side. So 2drl is the resisting area. Walls are resisting this force, so stress will be induced on the cylinder walls. So stress into this resisting area will give the resisting force. Stress induced, let us take it as sigma c, hoop stress induced there, into the resisting area, that is 2drl. So let us take that stress as sigma c into 2drl, that will give the resisting force. So sigma c into 2drl is a resisting force due to the stress induced, So that is equal to the bursting force. Or you can say stress induced, hoop stress induced, there is bursting force divided by area. So the area is 2 DRL. DRL is the one side resisting area. 2 DRL is the total resisting area of the cylinder wall. So this will give the hoop stress induced at a radius r. So hoop stress is going to vary. That's why we have taken an elemental ring and obtained an expression for hoop stress. Now we will divide this by 2 DRL. So 2 DRL will cancels. You get minus PR. And 2 DRL if you divide, 2L will cancels. You get minus R dPr by dr. So sigma C will get minus PR minus R dPr by dr. This is one of the equation. Okay. So this gives a relation between hoop stress at a radius r and radial pressure transmitted PR. Okay. Now longitudinal strain induced in the cylinder walls is given by this expression. Now on this thin cylindrical shell, let us take a small element on the cylinder surface. It is subjected to longitudinal stress sigma L, circumferential stress sigma C, and also radial pressure PR. From inside PR, outside PR plus dPr, I have taken its PR, neglecting that small variation. So it is subjected to say compressive force. In case of thin cylinder, we did not take this radial pressure because that radial pressure is small in case of a thin cylinder. So thick cylinder, this radial pressure, that is deformations due to this radial pressure cannot be neglected. So due to this compression, there will be a change in length and reduction in thickness of the cylinder wall. So this radial pressure we cannot neglect. So in thick cylinder, that radial pressure is also considered. So there are three stresses acting. One is a longitudinal stress, another one is circumferential stress, and this radial pressure. Radial pressure is also inducing stress. The transmitted pressure is stress. So this is a compressive stress. So three directions stresses are acting. So you can find out the strain in the longitudinal direction. Strain in the longitudinal direction you can write as sigma L by E. Due to this hoop stress, it will induce a lateral strain, that is minus nu sigma C by E, and due to this radial pressure there will be a lateral strain in this direction, that is plus nu PR by E, plus because it is a compressive. The regular expression is Ex is equal to sigma x by E minus nu sigma y by E minus nu sigma z by E. Since sigma z is minus PR, minus of minus will make it is plus. Okay, sigma x is sigma L, sigma y is sigma C, and sigma z is minus PR. Okay, so that give this expression. So on the cylinder wall, the stresses acting is shown, and applying the generalized Hooke's law, you can get the longitudinal strain on the cylinder wall as sigma L by E due to direct strain, and due to this lateral strain is minus nu sigma C by E, and due to this compressive stress plus nu PR by E. Now this longitudinal stress and longitudinal strain is more or less constant on a cylinder wall. Any radius, if you take, the longitudinal stress is more or less same on a cylinder wall, and even the longitudinal strain, that is on the inner cylinder wall or outer cylinder wall, as the radius changes, the longitudinal stress is not going to change much, only the hoop stress is varying. So the stretching on the inside cylinder wall or outside cylinder wall will remain same, or longitudinal strain will remain same. Each fiber on the inner surface or outer surface will stretch equally on the cylinder wall. in the longitudinal direction. So longitudinal strain is same and longitudinal stress is also constant. So since this longitudinal stress and longitudinal strains are constant, so this term is constant, this is constant. So since these two quantities are constant, this summation has to be a constant. So minus mu sigma c by E plus mu PR by E is a constant. The entire equation, if you divide by minus mu by E, you will get sigma c minus PR is a constant. This constant I will write it as 2a, or sigma c minus PR is equal to 2a, or sigma c is equal to PR plus 2a, where a is another constant. So we will get sigma c, that's which is the hoop stress at a radius r, is equal to radial pressure at a radius r plus 2 times a constant. So this is a second equation. So you have a first equation, relation between sigma c and radial pressure, and we have another equation on sigma c and radial pressure. Now this we can substitute, sigma c we can substitute as PR plus 2a. So you will get PR plus 2a is equal to minus PR minus r dpr by dr. So combining this 1 and 2, PR plus 2a is equal to minus PR minus r dpr by dr. Now minus PR will take left hand side, you get 2 PR plus 2a is equal to minus r dpr by dr. Now 2 into PR plus a, 2 is taken outside, 2 into PR plus a is equal to minus r dpr by dr. Now if you separate the variable, you get dpr by PR plus a, dpr by, I have taken this PR plus a down, you will get minus 2 dr, minus is taken, 2 into dr divided by r. Now if you integrate this, log PR plus a is equal to minus 2 log r, 1 by r integration is log r, log to the base e, natural logarithm. So log PR plus a is equal to minus 2 log r plus a constant of integration. Now this constant I will put it in a different form. So I will write it as a log b, where b is another constant and log b is also a constant. So b is another constant. This is to get the expression in a standard form. Okay, so log PR plus a is equal to minus 2 log r plus log b. Minus 2 log r you can write it as log r raised to minus 2, log r raised to minus 2 plus log b. Now log r raised to minus 2 plus log b, you can write it as log br raised to minus 2, log a plus log b, log a into b, so it's b r raised to minus 2. Okay. Now since log of PR plus a is equal to log of br raised to minus 2, you can equate that arguments, PR plus a is equal to PR raised to minus 2, or PR is equal to, this b r raised to minus 2 means b by r square, and plus a I have taken to the right hand side, so minus a, you get PR is equal to b by r square minus a. So radial pressure PR is equal to b by r square minus a, where r is the radius and b and a are constants. So you get the radial pressure as b by r square minus a. So once you get the radial pressure, we know the relation between radial pressure and hoop stress. So we have sigma cs PR plus 2a. So we got PR. Now to that, if you add 2a, you will get sigma c. So PR is this, you just add 2a to that, so this plus 2a, so you will get sigma cs b by r square minus a plus 2a. Okay, so we will get b by r square plus a. So sigma c is going to be b by r square plus a. These expressions are known as Lame's equation for the thick cylinder. So PR is equal to b by r square minus a, and sigma c is equal to v by r square plus a. So Lame's equation for thick cylinder is Pr is b by r square minus a and sigma c is b by r square plus a. So hoop stress is varying with respect to radius, and even the radial pressure is varying with respect to radius, and its variation is parabolic because the equation is parabolic equation. So hoop stress is varying parabolically, and even radial pressure is varying parabolically across the cylinder walls. So with the radius, hoop stress and radial pressure are varying. That's all for today. Thank you for watching.